Okay, so we spoke about before the break. We look at the data from Materials Handbook and what does this data show us. Okay, so what you will see that the data or the the properties or the mechanical properties were obtained in uniaxial or unidirectional test. Okay. What do I mean? What do we mean by unidirectional? So you can see we have tension, compression, and shear. So if they were to report any tests in tension or data or properties in tension, okay. So this is our material. We put it in tension. Okay. And the tension is the most commonly used, okay, due to easy setup or experimental setup. Okay, so in tension. Then the next most commonly used is compression. Okay, again, you have a material over here. Right, then you have it in compression. Okay, so for this case, compression usually are used for usually used for brittle material. Okay, so brittle material cannot withstand tensile stresses. Okay, used for brittle material. They usually do compression tests. Okay, or brittle material. What else? They are usually brittle material. And then the last one is shearing. Okay, so shearing, what they would tend to do is they induce a torque. Okay, where T is the torque. Okay, so for this case, they usually induce the torque. Okay, so this is the least commonly used. Okay, that is why when you look at this data, the most commonly shown are the tension, yes or no? Shear, you only have one out of so many, and for that reason. Now, how does all this, right? How does all these tests that we see relate to our principal stress? Okay. So if we look at our structure, it is not loaded in uniaxial, right? So we realize that this is not loaded in directional loading condition or unidirectional condition, right? It is not. You have shearing stress, like you see over here. You have shearing stress and you have normal stress, and the normal stress or the shearing stress are due to a formula like this, and the normal stress are due to a formula like what you see over here. Okay, they're not the loaded the same as what is seen on your material handbook, right? So the only way to relate them is to use what? Principal stress. Okay. So only way to compare stresses induced by non unidirectional loading and compare with materials handbook is to use principal stresses or maximum shearing stress. That's the only way. Okay. So you say that why is that? Okay. So what we see down here, right? All this value over here, you see. Okay, all this value you see, especially these two. So these two are your principal stresses. Okay, these two are your principal stresses. This is your maximum shearing stress. And I'll show you why. Okay, I'll show you why. Okay, because to become a computer engineer, right? These tests over here are loaded in uniaxial direction that you see on the table. Our structure that you see over here, right? This is not unidirectional at all. It's a compound loading structure. Okay. So the only way we can compare them is to use principal stress. Okay. So we understand from here, right? You know how to get, this is for compound loading, right? You know how to determine your principal stress, right? This principal stress you know how to determine now. This principal stress you also know how to determine. Now, how is this related to the principal stress over here? Okay, so let's look at a tensile. When we load a structure in tensile, how do we plot Mohs circle? Okay, so I'm going to draw tensile test. Tensile test. So in tensile test, right, and I'm going to sketch our centroid. And then this structure is being put P along the axis and our P prime. And then we're going to have an element at the center. Okay? This is our element. Okay, so I'm going to sketch out our element. So when this element is stressed, how does it look like? So I'm going to call this my X. Okay, so this will be our Y, and this direction will be our Z. Okay, so when we sketch this structure or stretch or apply load, what are the stresses that we can see? So in 3D, okay, I'm going to sketch this in 3D. So this is our element. right? This is our element. And we realize that element is only acting in this direction. Normal stress X. Okay, the rest is equal to 0. Okay, so for this case, it's only that stress X is not equal to 0. The rest, everything is equal to 0. So now when we plot our mole circle, right? So I'm going to label this our X. This will be our Z, right? And then the other face over here, I'm going to draw some hidden lines. Right, some hidden structure over here. Right, so this face over here will be our Y. Okay, so now when we plot mole circle, it looks like this. So I'm going to this is our normal stress, and this is our shearing stress. Right, rotate clockwise, anti-clockwise, and we know at this point over here, this is where our point Y and point Z are, 0 stress. And at this point over here, this is our point X. Okay, so now when we draw a circle, right, this is how it looks when we plot our mole circle now. So this point over here is our stress 1, and this point over here is our stress 2. And once again, you can see that stress 1 and 2 are the principal stresses. Where the shear stress is equal to 0. Okay. Now this is 3D mole circle. 3D mole circle can also be one circle, not necessarily has to be 3 circles. Okay. So if we look at our structure over here, our compound loading structure, we also have 2 stress points that have 0 stresses, which is our principal stresses. So we compare the what? Principal stresses from our loading condition and the principal stresses from the material handbook. Okay, so this is for tension. Now I'm going to sketch what if we have compression. Okay, what if we have compression test. Okay, so if we have compression test, how does it look like? So I just need to like copy this thing over. Right, so copy this thing over. So now rather than it pulling outwards, I have it pushing inwards now. And then I just need to flip the direction around. Right, that is our stress X. So now if we were to construct mole circle again, you'll see very similar. Okay, so this is our normal stress, shearing stress. So this is our normal stress, shearing stress, element rotate clockwise, element rotate anti-clockwise. So over here, this one over here is for our point Y and our point Z. And over here, this is our point X. Okay, so now we can construct another circle. All right, this is our circle. And again, over here, this is our stress 1. Over here, that is our stress 2. Okay, so what we see in our tension test, okay, and a tension either in ultimate strength or yield strength, is our principal stresses. The other value is equal to what? 0. No point reporting. Okay. So this is how we get